Hi, so we're going to talk about logistic regression as a classifier, which is not the way you learned about it in biostatistics, but I think it's very instructive to learning how logistic regression modeling works and how most models are pretty lousy at classifying people with regard to a characteristic or not. So we're going to review sensitivity, specificity, positive and negative predictive values. We're going to understand distinction between use of logistic regression for risk prediction versus classification, understand how receiver operating characteristic or ROC curves can be used to evaluate model classification performance, and understand the limitations of logistic as a classifier. So first, let's review validity. The ability, which is defined by Ziclo and Nito as the ability of a test to distinguish between who has a disease and who does not. We can think of logistic regression as a test for classifying people who have a characteristic or not based on some set of values. So recall 2x2 table for setting up and calculating measures of validity, and we can also calculate these from logistic regression. Sensitivity and specificity are two main measures, and sensitivity is the ability of a test to correctly classify all those who truly have the disease as having the disease. So it's the proportion of true positives over all the people who actually have a disease or characteristic. And specificity is the ability of a test to correctly classify all of those who truly don't have the disease as not having the disease, or the proportion of true negatives over all the people who are negative for the disease or characteristic. Positive and predictive value, I like to think of these as row calculations because we only use rows to calculate these values versus sensitivity and specificity where we only use columns. So positive predictive value is the proportion of positive tests that are truly positive. So they truly have the condition. Negative predictive value is the proportion of negative tests that are truly negative. So the probability that a test is that you are truly negative if you test negative for a test by the test. So anytime we're developing a test using a continuous variable, we need to set cut points. So let's use this example here. We're going to say we want to classify people with diabetes or without diabetes according to blood glucose, which is a continuous variable. So in the red distribution, we have people without the health outcome, and the specificity is the area under the curve to the left of this some cutoff value that we set. And the gray distribution is the distribution of blood glucose in people with diabetes. So the sensitivity is the area under the curve to the right of the cutoff value. So we can see to the right of this cutoff value, some people have blood glucose values who actually don't have diabetes. These are our false positives. And to the left of this cutoff value or criterion of positivity, we have people with blood glucose values that actually have diabetes. So these are our false negatives. We can move this cut point to the left to capture more of people with diabetes. But if we do that, we actually decrease our specificity. If we move it to the right to eliminate false positives, we actually increase our specificity but reduce our sensitivity. So there's always a trade-off between those two. So in regression modeling, we can use it in two ways. We can use it for prediction, which is a tendency of whether a condition or a set of condition poses a higher or lower risk of a characteristic. We can also use it for classification. To classify, we can use a model like in the example I just showed you for diabetes to classify people as having a characteristic or not based on a set of conditions that they have. In epidemiology and biostatistics, most of our work deals with prediction or associations rather than classification, because most of our public health problems are pretty complex, and it's hard to accurately classify people based on a set of variables as having a characteristic or not. And this is summed up in this quote here from Frank Harrell: when close calls are possible, or when there is inherent randomness to the outcomes, which is present with most of the conditions we work with, probability estimates are called for. So we can use a logistic regression model to help distinguish between those who have a characteristic and those who do not have a characteristic. In this case, we're using it as a classifier rather than a model to estimate associations between an exposure and an outcome. We can evaluate the validity or the sensitivity and specificity of the model using different measures. We can also use it for positive predictive value, accuracy, and we can use something called receiver operating curves to evaluate its validity, and also AUC values, or area under the curve values, which we'll get into. So a simple example of how logistic regression could be used as a classifier is for email. So if we have a test set of email, or actually a training set, we usually have a training set and that we train a classifier based on. So we could take a spreadsheet of emails and have individuals classify them by reading them as spam or not spam, and then we could identify certain characteristics that were present in spam emails versus not spam emails that help us develop a logistic regression model to classify emails as spam or not spam. So once we have that model developed, we can apply it to a real world situation and use it to, without having somebody read the email and classify it, use it to classify automatically emails as spam or not spam. A medical example for opioid misuse or not, where logistic regression use, is shown at the link here that you can look at if you want to see how this is applied in a more of a public health setting. So in the demo, we're going to use logistic regression as a classifier for diabetes in the BRFSS data set in the next video.